Hi everyone, welcome to Team 22's presentation of a potential xylene chemical plant we've been researched for a couple months. My name is Jialong Wang, and my teammates are Drew Carson, Emily Helm, Matt Longlot, Scott Schneider, and Yifei Huang. In this presentation, we're going to talk about the thoughts behind our design goals, design process, and the economic viability of our design. The plant is going to be added to an existing facility of Nitline Chemical Company, which is located on a Gulf Coast of Houston, Texas. The plant is located on a ship channel, so the production facility have the access to the pipelines for material supply. Therefore, it can reduce our transportation cost. And the design team operate out at the State College, Pennsylvania. The desired reaction of the process is toluene disproportionation, which converts toluene into equimolar amount of benzene and mixed xylene isotope. There are two major side reactions. The first one is toluene hydroalkylation, which produces benzene and methane. And the second one is xylene disproportionation, which produces toluene and 1,2,4-trimethylbenzene.
So for this project, we were assigned a given toluene feedstock flow rate of 65,600 pounds per hour. However, in our sensitivity analyses, we did consider other flow rates, and we considered what this effect would be on our profit and other design processes. So for this flow rate, for this feedstock, it was a mixture of 99.5 mass percent toluene, so mostly is toluene. However, we did have to consider the fact that it had 0.5 mass percent benzene as well. This toluene came from a storage outside battery limits tank about a mile away from our plant, kept at 15 psia and 80 degrees Fahrenheit. We also were allowed to use fresh hydrogen. The flow rate was not set for that. We were able to choose that flow rate. This was coming from a pipeline at 700 psia and 80 degrees Fahrenheit. The hydrogen also was not 100% pure. We also had to consider the fact that there was 10% by weight methane in the feedstock as well. For our project, we were given reactor data from a pilot plant, which we used to model our process in Aspen. We were able to get our full-size plant data from this. At 650 degrees Fahrenheit, this WHSV versus the mass fraction of paraxylene is shown on this graph. So it can be seen that our full-size plant data is a little bit more conservative than the actual reactor data. However, it does follow the same trends, which is good. So we also chose a WHSV of 0.1 for our actual process, which means that we have a lot of catalysts this means that we have a lot of catalysts per our flow rate going into the reactor. So this was done because when examining conversion versus selectivity, this had the best trade-off. It maximized conversion with selectivity. From our design and process, we were able to the product purity hard specs that were assigned to us for the process of having a benzene and paraxylene product that is at least 99.9% mass purity. So we matched that, which shows that we were successful in our endeavors, and we did this through all the unit operations, such as distillation, flash, and the Parex column.
Most of the soft specifications were met for the process. The total light in the reactor feed was kept under 15% weight. The hydrogen purity in the inlet and outlet of the pressure swing unit were in spec. Also, the partial pressure of hydrogen in the reactor feed was kept at 250 psi. However, the target toluene recovery, 85%, was not met. In addition, the molar hydrogen to toluene ratio in the reactor feed was kept at 2. However, xylene and benzene in the reactor feed was above the desired percentage. Also, the total loss of benzene, toluene, and p-xylene was 5%, which is larger than the desired 3%. However, this could also be due to that we're selling part of the p-xylene in the mixed xylene stream. The soft specs were not meeting demand extensive purification. Achieving such high purity would increase the cost of separation significantly. As these soft specs don't affect our product purity, we decided that the current process is the most economic. The plant employs control mechanisms and relief valves to maintain safety. As most of the process streams are in vapor phase, pressure control is very important. We placed a relief valve on all major operation units. As the process chemicals were not considered immediately toxic, we decided that it is acceptable to vent the vapor into atmosphere in case of emergency. In addition, pressure controls were added to all the distillation columns. Level controls were added to all liquid tanks and distillation columns. Temperature controls were placed around all heat exchangers. The plant is environmentally friendly because it does not utilize a flare system. Flammable byproducts are sent to a vapor fuel system for future use instead of being burned directly.
All right, so this process includes 8 unit operations to produce our desired products. So coming into our plant, we have 2 fresh streams that are hydrogen and methane and toluene. Those streams are met and mixed with a toluene recycle stream and a hydrogen recycle stream. All 4 of those streams enter our reactor, which is sized at roughly 25 feet in diameter by 44 feet in length. After exiting the reactor, our product effluent goes through a heat exchanger before column 1 and goes through the column 3 reboiler. We sent our product effluent through those 2 units to save on the waste heat. Then the product effluent goes to the flash stream, or flash column. In the flash column, the hydrogen and methane are split and sent out of the top of the flash. It goes to the pressure swing column where hydrogen is purified and then sent back in the hydrogen recycle stream to the feed. The bottoms from flash 1 then go to column 1. In column 1, toluene and benzene are sent to the distillate, and the bottoms of column 1 consist of our mixed xylene isomers and our trimethylbenzene. After column 1, we see a unit of parallel distillation columns. These distillation columns are responsible for purifying our benzene in column 2, and in column 4 it is responsible for purifying our toluene before being sent back to the recycle stream. Column 3 separates the xylene isomers from 1,2,4-trimethylbenzene. The distillate from column 3 then goes to the Parex absorption unit. The Parex absorption unit uses fixed beds that separate the components based on molecular conformation. The top of the Parex absorption unit sends the paraxylene isomers to either the product stream or to be recycled before the Parex unit. 20% of the Parex unit product is sent back to be purified again through the column. This increases our paraxylene purity and also our flow rate of our paraxylene product. The bottoms from the Parex unit are sent to the OBL system as mixed xylene isomers, where they will be sold for a less percentage than the paraxylene isomers. Our yearly raw material costs totaled $149 million. On a cents per pound product basis, toluene is by far our largest raw material cost, coming in at 106 cents per pound. Our other raw material costs are our catalyst, which is 9 cents per pound product, miscellaneous chemicals, which are 3 cents per pound product, and hydrogen, which is 4 cents per pound product.
IVL equipment was then inputted into Icarus to determine the final capital costs. These totaled to $51 million. 42% of this total cost was just for columns and flash, but the reactor actually had the largest per unit cost. It took 39% of our $51 million. Utility costs per year totaled $19 million. This included high pressure steam, medium pressure steam, cooling water, diatherm hot oil, refrigeration, and power. And from this pie chart, you can see that high pressure steam and diatherm oil took approximately 75% of this cost. So in the future, the design should be altered to utilize more low pressure steam and medium pressure steam as a preheating utility so that less high pressure steam and diatherm oil have to be used in the future. This would actually decrease utility costs by approximately $1 million per year from one of our alternative studies. It could probably be lowered even more in the future. Per each pound of product produced, 10 cents went to fixed costs, including labor, overhead, repair and maintenance, property tax, and insurance. And you can see that each of these was a significant amount of our fixed cost. Product revenue per year totaled $200 million. This came from benzene, paraxylene, mixed xylenes, and an additional fuel credit from our vapor fuel system. You can see from the pie chart that benzene was the product that we received the most revenue from at 46%, followed by paraxylene. In the future, we would like to try to alter our reactor with maybe a different WHSV or a different temperature to increase the amount of paraxylene produced and limit the amount of benzene produced.
Our ATRR value was currently unable to be calculated at our product price of 48.3 cents per pound. For the first 3 years of our plant, we're predicting a sharp decrease in our cumulative cash flow, which is due to our initial capital costs. Over the remaining 12 years, we're still steadily losing profit over these years. Due to the constant decrease and no increase in profit, we're unable to calculate our ATRR value through any kind of prediction method. To obtain an ATRR value of 20%, we would have to have a product price that is much larger than what we currently have. A product price of 88.2 cents per pound would help us achieve this goal. This would also lead to a much higher cash flow for us, which is shown on the graph, where at the year 2026, only 6 years after production, we start to make a positive cumulative cash flow. Assuming an ATRR of 20%, a positive cumulative present worth is obtained by the year 2029. In our current conditions, we are not able to achieve this value. However, if the pricing of paraxylene were different and we're at 88.3 cents per pound like we previously mentioned, this would be possible. Additionally, if we ended up having a lower utility rate or a lower fixed costs, we would also be able to achieve a higher ATRR value. Our total ongoing costs are made up of mostly raw materials, accounting for 124 cents per pound product. Our raw materials are largely made up of our toluene product, as well as a small amount of hydrogen. Other main costs in this project were our utilities costs, which make up 10% of the total cost as well. Other costs, including labor, SG&A costs, and property tax, make up only 4% of our total ongoing costs. To become profitable, our catalyst costs must be reduced to a smaller percentage of our current point estimate. Currently, our catalyst costs are 34% of our current point estimate. This is the largest value that we're able to kind of work with, since our total contractor cost is a largely invariable value. For our 34%, this is due to we have a very low WHSV currently at 0.1. If we increased our WHSV to a higher value, we could likely use a lot less catalyst and would have a lot smaller cost in this area.